Now, this method, the second method we are discussing here is the inverse CDF method. Okay. It uses the very interesting property of the CDF. Now, what you're looking at is this. So if you are able to take a very small interval on the y-axis in the CDF and look at what are the probability that the CDF is actually within that range, right? So you basically draw horizontal lines of that the interval that intersect with the CDF function, and then vertical lines down here. So if you have something, if you have a random variable that's distributed according to this exponential distribution, right? The probability that my x is greater greater than the left axis, the left is greater than the left interval and less than the right boundary, is actually equal to the value of the CDF on the right minus the value of the CDF on the left, right? So if I have an interval a and b, right, the probability of a less than x less than b, that's an event, right, is actually the CDF of b minus CDF of a, which is the width of this interval, right? The width of this interval is the probability that x lies in that range. So we use the clever trick that actually, instead of sampling x, I'm going to be sampling the CDF of x. Okay, what that means? What it means is that I'm going to be sampling the yi, y1, y2, etc., yn, okay, so that each yi is equal to the CDF of xi. Why is that useful? Well, it is useful because if xi follows the desired distribution of x, then what does yi follow? I mean, what does y follow? What distribution does y follow? Okay, the probability that my yi is less than a is actually going to be what? Is the probability that my CDF of xi less than a. Okay. So basically, that is saying yi follows a uniform distribution, right? Okay, so basically, the probability that yi less or equal to a is actually equal to a itself. So if I can sample these y's and then I follow the definition of y and take xi equal to the inverse CDF of yi, then I get a set of xi's that are distributed according to the desired distribution. All right, so let's see how that works in practice. So again, we have x. Now this time we want an exponential distribution. Let's start with a lambda equal to 1. Okay, and if lambda equal to 1, what is my inverse CDF? if lambda is equal to 1, I have the CDF being this, okay? And my inverse of the CDF, let's say if y is equal to 1 minus e to the minus lambda x, right? If I want to figure out what's the inverse CDF, I want to figure out what is the function x as a function of y. So arrange the two sides. We have e to the minus lambda x would be equal to, let's move to the left-hand side and move y to the right-hand side. I have equal to 1 minus y. So minus lambda x would be equal to log of 1 minus y, which means x would be equal to minus 1 over lambda log 1 minus y. That's my inverse CDF. Okay, so let's do it. Let's clear everything, and I want to sample y as a uniform distribution. So let's perform a million samples of y and apply the inverse CDF. So if lambda is equal to 1, then minus 1 times log of 1 minus y, right? That's my x. And let's take a histogram of x with 100 samples to see what that gives me. Let's close all so that we don't interfere. That's a nice exponential distribution here, right? As you can see that as my x increases beyond 1, the number of samples are less and less. And ultimately, it stops around the 14-ish because the probability I'm getting any sample beyond that is so small that even with a million samples, I did not get any samples that large. But in reality, the probability is still non-zero, right? It's getting smaller and smaller, but never becomes 0. Okay, so what if, for example, we decrease lambda to, let's say, 1 over 100, right? If we decrease lambda, the tail of the distribution is shifted, it's increased, right? So if you look at the PDF formula, if lambda is 100th, that means the probability that x is around 0 is decreased, but the probability when x is bigger is actually increased by a lot. So we expect the tail to be longer. That's my x, let's say x with 100th, x2 is equal to minus 1 over 100. So that's my lambda. And times well, it's 1 over lambda. So if lambda is 100th, this is actually minus 100 times log of 1 minus y, right? So, and if I hit the x2, you're gonna see that the distribution is shifted. It's really multiplied by a factor of 100. We have a much longer tail. Instead of about 14, we get to 1400. So this is how we are sampling infinite distribution.